Hi everyone. So this is a review worksheet where we're going to cover phases of matter and the energy associated with them. So before getting started, I just want to say that if you can keep the particle drawings in mind throughout this entire assignment and throughout the future in the quiz and the homeworks and you know continuing to build on our knowledge here, that's really going to help you. So drawing these right now is going to be really important for your understanding of a lot of the stuff we're going to talk about in the coming weeks in chemistry.
So let's go ahead and jump in. We're reviewing the phases of matter and the energy that is associated with it. So what even is matter? Well, matter is everything, right? And we have three states that we mostly see and interact with in our world and in our lives. We have solids, liquids, and gases. So I'm not sure if you've seen this abbreviation in your textbooks yet, but solids are normally abbreviated with the S, and these are all lowercase, and they're usually enclosed in parentheses like this. Liquid is an L, and it's usually written in cursive, so a cursive lowercase l, and then a lowercase g for gas. All right, and throughout we're going to use water as a substance that we're comparing these phases of matter because we're all familiar with water, right? Water's solid state is ice, liquid state is what we call water, right? It's what we drink. And then the gas state of water is gas vapor, or usually we see that as steam. Okay, and this is what we can see with our eyes. We can actually see ice, water, and steam, right? But what we're going to be talking about today is at the very, very, very zoomed in level of the atomic or molecular level. All right, so what these circles here are depicting is the particle diagrams. So like right here is one particle of water, right? This is one particle of water. This is one molecule of water. So our solids are going to be very compact and organized together, very packed in there. As you can see, they're all touching each other. They're very organized and they're moving very slowly. Our liquids are going to be more spaced apart. Our molecules are more spaced apart here. They're a little more fluid. They're free to move around a little bit more than in the solid phase. And they have a little bit more movement than they do in the solid phase, right? And then our gas molecules are very spaced apart. They are taking up whatever the shape of the container is, and they're moving very fast, right? Remember, they're zipping around all the time. These gas molecules are very spaced apart, and there's lots of empty space in between them, and the way they move is with, rapid, straight line, random movements. Okay, and they bounce off of the walls of containers when they run into them. Okay, so those are our phases of matter, our three states of matter that we're going to talk about. So now that we've covered that, we know our three states of matter, we can talk about the energy that is associated with them. And remember, we're talking about the movement energy, and that is called kinetic energy. These we're going to first draw our particle diagrams. So here we're going to do solid, liquid, and gas. And what I want you to do is draw what our particle diagrams look like. Imagine that we're still contained in that flask, all right? So what a solid is going to look like, we're just going to use circles for each molecule. You don't have to draw all the atoms in the molecule, all right? So here's our solid. Pardon my horrible drawing skills on the computer. I think you guys are a lot better at this than I am. But here's our chunk of ice, essentially, super zoomed in, right? We have all of the molecules together, touching. Our liquid molecules are going to be more spaced out. They're still at the bottom, right? Because they take the shape of the container that they're in. So they're just spaced out, a little more fluid, a little more free to move around, right? Liquids are a little bit less organized than the solids, and then our gas molecules are going to be uniformly distributed throughout their container, and they're going to be rapidly, randomly moving around, right? I'm going to use these little arrows, not arrows, but lines to show that they have movement, okay? Okay, so with regards to the kinetic energy of each of these phases, we know that everything's always moving always, right? But our solids are going to have the lowest amount of energy. And I'm just going to put an arrow here. And then our gas are going to have the highest amount of energy. All right, so if we are changing phases and we're moving from a solid to a liquid to a gas, we can see here that the energy, the kinetic energy is going to increase as we move from a solid to a liquid, and it's going to increase some more as we move from a liquid to a gas, hence this arrow up at the top. Okay, so if we are moving from a solid to a liquid to a gas, we are obviously increasing our amount of energy that we have, right? So we can, right up here, we're going to write we're increasing in energy. We are gaining energy as we move from these phases. So what we call that is endothermic. So remember we have those terms, endothermic and exothermic. Endo you can think of as coming inside, right? And exo is outside, it's releasing. So endo means, you're bringing it in, you're gaining energy. And where does that energy come from? What even is energy, right? Well, in this context, we're talking about heat. We're talking about heat. That is energy, right? So we're gaining energy. Think about if you're going from a solid to a liquid. In our water context, we're going from ice to water, to liquid water, okay? So we are requiring heat or energy for that. So we're calling this endothermic. So anything that is going in this direction from a solid to a liquid to a gas, following this arrow is taking in energy. Okay, so we have it stated as increasing in energy. E is just short for energy. It is endothermic, and that also means it's taking in energy. So going from a solid to a liquid, we're taking in energy from the environment, right? We are adding more energy to our molecules here. That's why they're more spaced out, and that's why they're moving. Okay, we're going from a liquid to a gas, we are taking in more energy. Okay, it is endothermic, and consequently, if we were to jump from a solid over the liquid to a gas, we would need a lot more energy, but we're still taking in energy, and that's why it's categorized as endothermic. And I just realized that I forgot to play this for you. But essentially, at the molecular level, this is what all solids, liquids, and gases look like. Okay? Everything's always moving. You can see solids, they're solid, but the particles are still moving. Okay, liquids are moving faster, they're more loosely organized, and the gases, they're just going crazy over there. They're just zipping and flying around. They've got the most kinetic energy, they're moving the fastest, and they are the least organized. Okay, so you can just tell from this diagram that going from a solid to a liquid, we're increasing the kinetic or the movement energy. Remember, kinetic means movement. Okay, so what if we're going in the opposite direction? What if we're going from a gas to a liquid and we're going this way? Well, it's basically just the opposite. Okay, and if we go from a liquid to a solid, basically just the opposite. We are losing energy, okay? We are going from crazy gas molecules flying, zipping around, they don't care, right? To becoming more organized and trapped. Like, let's draw like a little liquid layer here. We're just putting waves because that's essentially how you recognize that it's a liquid, right? Okay, so we're going from these gas free-flying molecules are flying around everywhere. They don't have any rules, right? They're just bouncing around, flying as fast as they can. There's no organization there. And then we are bringing them to this liquid state where there's a lot more organization. So we're actually decreasing the amount of kinetic energy here. Consequently, they're also slowing down, okay? Our gas molecules are super fast flying around, they're slowing down in the liquid stage, and then when liquids move to solids, they are slowing down to even more to this fixed state and shape, right? But they're still moving, they just have the lowest amount of energy. So we're losing energy. Let me get my text box over here. We're losing energy. Losing energy, they are giving off energy, they're releasing energy, right? Those are all ways to say the same thing, that they are exothermic phase changes, okay? Exo, remember, means on the outside, right? Think of an exoskeleton. So they are giving energy away. They are taking energy and giving it away. They're releasing it to the environment, all right? Releasing energy to environment. So for this next part, I want you to keep in mind these particle diagrams here, okay? If we are going from a liquid to a gas, you can look right here, and if you can't think of it off the top of your head, look right here. We're increasing energy, so that means it's going to be endothermic, okay? If we're going from a gas to a liquid, we are decreasing energy. If we're going liquid to solid, we are decreasing. Follow your arrows, right? We're losing energy. We're calling that exothermic, okay? Because we're slowing down. So at any point during any phase change, we're either gaining or losing energy. Gaining or losing kinetic energy. So that is always going to be labeled as endothermic or exothermic. So use your drawings here for this next part. Page 2 of this review worksheet, we are going to be naming each of the phase changes and labeling the associated energy change. Is it endothermic or is it exothermic? But first, just to review, we are doing phase changes, and are phase changes physical or are they chemical changes? Are we changing the matter at all? No, we're not. We're just changing the state of it, okay? We're melting ice into liquid water, or we're boiling liquid water into steam. It's still water, it's still H2O at the fundamental level, so there are no physical changes. So here I am going to put physical. The only difference between these samples is a distance between the particles and how fast they are moving. Okay, so they're physical changes, not chemical changes. All right, these are just phase changes. We're not talking about chemical reactions or anything crazy complex here, just the energy and the movement between going from one phase to another. All right. Okay, so here's the deal. You need to know this. You need to know the names of each of these phase changes. You need to know the energy changes associated with them. This is going to be on the quiz, all of this. Okay, so you can use this as you're filling out this chart, but what I want you to think about every time you see one of these is look at the particles. Are they moving closer together? Or in this one, they're actually moving farther apart. So what does that mean? They must have more kinetic or movement energy, right? So this first one, going from a solid to a liquid, what are we going to call that if we are increasing our energy? Well, we can go look up here. Going from a solid to a liquid, we're increasing energy, so we're going to call that endothermic, okay? Energy change is endothermic. And also want to mention for each one of these, I have a little snippet GIF for you to see, so you can just hit play. You can maximize it if you want. So this is just melting, right? I just gave you the answer, but this is a solid piece of ice melting into a liquid form of water here.